Good afternoon. Anybody has joined? Hello?
Yes, sir.
Okay. So how many students have joined?
So around 24.
Okay. So last class we were discussing some problem on transportation problem. So as I told, I will repeat few more problems. So the basic concept is like this. So we have a transportation model. The transportation model is a special type of linear programming problem, but we don't apply directly the simplex method to solve the problem. So we apply the simplex procedure, simplex rule to solve the problem. Okay, and here, so the duality theory is playing a major role for finding the phase 2 solution. So using the northwest corner rule or the least cost method, so we are finding the trial solution. This trial solution is a feasible solution, basic feasible solution, but it may not be optimal. So using the duality theory, we'll test whether the solution is optimal or not. If it is not optimal, we'll find a improved solution. So I'm repeating again the mathematical model. As you know, for the transportation problem, it is always minimization type. So this is a two index problem. Two index means the variables. So subscript with the I and j. I varies from 1 to m and j varies from 1 to n. That is, we say minimize z equal to summation over I varies from 1 to m and j varies from 1 to n, Cij xij. The Cij, the cost coefficients, cost of transporting, say, 1 unit of product from ith source to jth destination, the cost is given. This xij is the unknown. We are interested to find the xij. There are, in this problem, there are m into n number of variables, decision variables. So we will find all the decision variables, some are 0 and some are non-zero. So in this problem, there are m plus n number of equally type constraints. So in the dual problem, if you are finding the dual, we have m plus n number of dual variable, but since they are equally type constraints in the primal problem, the dual variables are free variables. So we'll utilize the conditions to find the dual variables. So, and we are, instead of naming the dual variables y1, y2, etc., we are giving different names, something like say u1, u2, um, and v1, v2, vn, etc. So I will mention why we are using so. So this transportation problem, we say it is balanced if sum of I varies from 1 to m AIE, that is amounts of the product available at the factory equal to sum of the demands, that is j varies from 1 to n bj. If they are equal, then the problem is called balanced. If the problem is unbalanced, we can make it balanced. Sometimes we add a fictitious source, or sometimes we add a fictitious destination. But generally, the problem is given as balanced. So we'll solve a balanced transportation problem. Okay. So generally, as I mentioned, the problems are always minimization type, not maximization type. And all the constants are equally type. Okay. And it has m plus n number of constraints and m into n number of variables. This. So with respect to the present problem, if you are finding the dual problem, say the dual is a maximization type problem. So it has m plus n number of dual variables. So we like to maximize z dash, summation over I varies from 1 to m, ui into ai with respect to the source constraints. And we have summation over j varies from 1 to n, bj into bj with respect to the destination constraints. And here You see, we are writing. Hello? Any problem? Hello? Do you feel any problem?
No, sir.
Okay. Subject to ui plus vj less than equal to cij. And now the question is how we are able to write. I will just explain using a small example. Ui plus vj less than equal to cij. Okay. So as you know, we are finding the dual of a linear programming problem. If the primal one is maximization type, the dual one was minimization type. If the primal is minimization type, dual is maximization type. So all the rules we have it is known to us. So we will apply all the rules to find the dual of the primal problem. The dual is like this: maximize z dash, summation over I varies from 1 to m, ui into ai plus summation over j varies from 1 to n, vj into bj, subject to ui plus vj less than equal to cij. And I varies from 1 to m, j varies from 1 to n. So altogether, how many such constants are available? How many such constants are available? Who can say? Ui plus bj less than equal to cij. I varies from 1 to m, j varies from 1 to n. How many such constants are available?
M into n.
M into n number of constants. Okay, m into n number of constants. Because the primal problem has m into n number of variables. With respect to the primal problem, the dual problem has m into n number of constants. The constants are ui plus vj less than or equal to cij. The cij is known, the cost coefficient is known. Ui and vj are unknown, so you have to find out. Okay, these ui and vj are generally free variables. Free variables, they can be positive, negative, can be zero. Okay, so altogether we have m plus n number of free variables and m into n number of constants. Okay, all the variables, as I mentioned, they are free variables. Now, if I am considering instead of a 2x2 problem, if I am considering a 3x3 problem, so many information here you will visualize. M equal to 3, n equal to 3. The primal one is like this: minimize z equal to summation over I varies from 1 to 3, j varies from 1 to 3, cij, xij, subject to j varies from 1 to 3, xij equal to ai, I varies from 1 to 3. Then we have summation over I varies from 1 to 3, xij equal to bj, j varies from 1 to 3. So in this primal one, we have 9 variables. 9 primal variables, that is something like x11, x12, x13, x21, x22, x23, x31, x32, x33. And we have 3 plus 3. Yes?
One second, I need to.
You are saying something? Hello? Okay. There are altogether 3 plus 3, there are 6 equally type constants. With respect to source, there are 3 constants. With respect to destination, there are 3 constants. Altogether, there are 6 constants. And for this problem, one extra condition is imposed. It is a balanced transportation problem. Balanced means A1 plus A2 plus A3 equal to B1 plus B2 plus B3. Okay. So due to the balanced condition, out of the 6 constraints, only 5 constraints are linearly independent. So 5 constraints are linearly independent. We have a basic feasible solution having 5 non-zero variables. Out of 9, only 5 non-zero variables, rest are all 0. So now, with respect to this problem, if you are finding the dual of the transportation problem, we have maximized z dash, that is a1 u1 plus a2 u2 plus a3 u3 plus b1 v1 plus b2 v2 plus b3 v3, subject to ui plus bj less than or equal to cij, and I varies from 1 to 3, j varies from 1 to 3. Altogether, you can see here, there are 9 such constraints, 9 such inequation, they are constraints, and we have 6 dual variables. 6 dual variables. Dual variables are u1, u2, u3, v1, v2, v3. Okay. See carefully now for this problem. If I am finding the dual problem, okay, so I am renaming. See here, x11, x12, x13, 21, 22, 23, 31, 32, 33. These 9 variables I'm naming in this manner: x1, x2, x3, x4, x5, x6, x7, x8, x9. For example, I'm renaming x11 as x1, x12 as x2, x13 as x3, and similarly x33 as x9. Okay, these are the primal variables. Okay, now the dual variables are u1, u2, u3, v1, v2, v3. Okay, u1, u2, u3, v1, v2, v3. Now you can see here. So what the constant is given, say x11 plus x12 plus x13 equal to a1. Okay, so in the same row, only 3 elements are 1, 1, 1, rest all are 0. In the second row, you can see here, first 3 are 0, then next 3 are 1, 1, 1, then we have all 0, that is equal to a2. Okay, because we are naming something like this. So x21 plus x22 plus x23 equal to a2. So we are writing in this fashion. And similarly, the last constraints, source constant, first 3 are 0, then next 3 are 0, then next 3 are 1, 1, 1, something like x31, x32 plus x33 equal to a3. So we can name something like x7 plus x8 plus x9 equal to a3. Now, if you are presenting the destination constraint, something like we have here, x11 plus x21 plus x31 equal to b1. 1, then 2, 0, then 1, then another 2, 0, then 1, another 2, 0 equal to b1. So similarly, we have x12 plus x22 plus x32 equal to b2. So 0, then 1, then 2, 0, then 1, then 2, 0, then 1, then 0 equal to b2. Similarly, we have here x13, x23, x33. Okay, this is equal to b3. So 2, 0, then 1, then 2, 0, then 1. So in this fashion you can write. Okay, so how many variables, how many primal variables? There are 9 primal variables. How many dual variables? There are 6 dual variables. How many primal constants? There are 3 plus 3. Okay, so there are 3 plus 3, there are 6 equally type constants. So if you think about the dual problem, okay, so we want to find this dual constants. So you can see here u1 with respect to the u1 column wise u1, then u2 is not there, u3 is not there, then v1. u1 plus v1 is less than or equal to c1 in the top. Similarly, u1 plus v2 less than or equal to c12. Then we have u1 plus v3, okay, less than or equal to c13. In same manner, you can clearly you can write, okay, this. So there are 9 such inequations. They are the dual constants, and we have a dual objective function. What is the dual objective function? The dual objective function is something like here. We have, so maximize a1, u1, u1 is y1, a2 that is y2, y2 is our u2, a3 into y3 that is our, okay, so y3, and similarly b1, v1, b1 is our y4, b2, v2, b2 is our y5, and b3, v5, b3 that is our y6. In this manner we can write. So same manner we are presenting. So this is the dual problem. Okay, the dual problem. But very difficult to believe how this is happening. Okay, so here you can see ui, very easy to remember. Ui plus Vj is less than or equal to Cij, not greater, because minimization type, generally maximization type problems, the constants are less than or equal type. Minimization type problem, constants are generally we say greater than or equal type, but here it is equally type. They are so with respect to equally type, we have the free variables. So we will present in this manner. This maximization type dual program, minimization type primal program. These two conditions we are somehow using. Okay, how we are using, I will explain. Okay. Now let us consider a 3x3 problem. Let us consider a 3x3 problem. So, and this is a balanced transportation problem. Generally, a transportation problem is given in the matrix format, not in the equation format. So, what is here? So, there are 9 variables as you see, they are unknowns. Say x11, x12, x13, x21, 22, 23, 31, 32, 33. The 9 variables. These are the primal variables. And we have some cost coefficients. What is the cost? If you transport 1 unit of product from source 1 to destination 1, the cost is 1 unit, 1. You can see here 1, it is written in a within a box. Okay, 1, then next cost is 9, then next cost is 2, row wise I am talking, then the next cost is 3, then 8, then 4, then 5, 7, 6. So our objective function, we want to minimize as much as possible. How? We can write x11 into 1 plus 9 into x12 plus 2 into x13 plus 3 into x21 plus 8 into x22 plus 4 into x23 plus 5 into x31 plus 7 into x32 plus 6 into x33. This is our objective function, subject to their source constraints are like this. Okay, x11 plus x12 plus x13 equal to 7 unit, x21 plus x22 plus x23, this is equal to 9 unit, x31, x32, x33, this is equal to 14 unit, 7 plus 9, 16 plus 14, that is 30. And now the demand constants are like this, x11 plus x21 plus x31, this is equal to 10. Similarly, so here we have x12, then x22 plus x32, this is also equal to 10. Then similarly, x13, x23, x33, this is also equal to 10. So 10 plus 10 plus 10, 30, and that is also equal to 30. So this problem is a balanced transportation problem, balanced. Okay. Now, what is your aim? We like to find a solution. So this solution, as you know, the transportation problem we solve using 2 different phases. Why 2 different phases? So we'll find a trial solution, basic physical solution, and we'll test whether this given solution is optimal or not. If it is optimal, we'll stop. If it is not optimal, we'll try to improve using the Modi's method, the modified distribution method. Okay, that's all. Now, you can see here, with respect to this problem, we have a dual problem. Okay, so I am writing the dual problem also. Maximize Z dash, that is 7u1 plus 9u2 plus 14u3, 10v1 plus 10v2 plus 10v3, subject to, you know, there are 6, so 9 such pairs, u1 plus v1 less than equal to 1, u1 plus v2 less than equal to 9, u1 plus v3 less than equal to 2, etc. Okay, so there are 9 such constraints, and all these u and v, these multipliers, we are naming as u1, u2, u3, and v1, v2, v3. There are 6 in number. They are free variables. Okay, so As you know, due to the duality theory, the maximization of z dash is always less than equal to minimization of z. Minimization of z, this is always greater than equal to maximization of z dash. And in general, for optimal condition, for optimal solution, maximization of z dash equal to minimization of z. This second one will fulfill. This first one is called weak duality and second one is called strong duality. This, if it is fulfilled, then both the primal and duals, if it is optimal, and then this is fulfilled. If it is not optimal, generally this is true. Maximization of z dash less than, we can say strictly less, minimization z is not optimal. Okay, this. Now, this is the problem. We are finding a solution. We are finding a solution to this problem, that is a phase-wise solution using northwest corner rule. We are finding a trial solution or phase one solution using northwest corner rule. You can also apply least cost method. So both are similar procedures. So sometimes the least cost method gives better solution. So here we need any solution. So to start the next step, that is start the modified distribution method. You can see here. So according to this, this cell, the first cell is the northwest corner cell. So we will allocate as much as possible to this cell. Source one is 7 unit, destination is 10 unit. So we can maximum allocate 7 unit. So once you are allocating 7 unit, so only 3 units left out of 10. So 10 minus 7, that is 3. 3 is left. So see, the row 1 is fulfilled. Since row 1 is fulfilled, I can cross the, I can delete a, this is the first source I can delete. So if you delete the first source, again, the problem became balanced. However, there are 2 sources and 3 destinations balanced. So how it is balanced? How we can say balanced? So 7 has gone. So next is 9, then 14, 9 plus 14, 23. And we have 10 plus 10 plus 3, that is 23. So it is a balance problem. Okay. Now, once you have removed the first row, we will check which one is the northwest corner rule. So the cell numbers, that is 2-1, cell number 2-1, second row, first column. Okay, second row, that is becoming in the northwest corner. So how much it is available? Row wise, it is 9 unit, column wise 3 units. So maximum we can allocate 3 units. So once you allocate 3 units, the first column is can remove and you can reduce from the 9, say 3 units. So finally it is 6 units. Okay, this. So first column we have removed, first row we have removed, first column we have removed. Then ultimately, so this problem also remain balanced transportation problem with 2 sources and 2 destinations. So then cell number 22 is becoming the northwest corner cell. Cell number 22. So we will allot as much as possible. Row wise it is 6 unit available, column wise 10 unit. So we can allot 6 units. So then the second row we can remove, then we can reduce. So from 10, 6 units, only 4 units left. Okay. So finally, so once you are removing the second row, again you see here the cell number 32 is becoming the northwest corner cell. So how much you can allot? We can allot 4 unit. So that column is gone. So and you can reduce from 14. Then that is you can reduce 4 units. So ultimately, so you can see here. So 14 minus 4, that is 10. So ultimately in the last cell 3, we are allotting 10 units. Now here it is a question to you, how many allocations are there? In first row 1, cell 1 1. In second row 2 cells are allocated. That is cell 2 1, cell 2 2. In the third row we have 2 cells, cell 3 2 and 3 3. Altogether we have 1 plus 2 plus 2, 5 allocation. Altogether there are 5 allocation. Out of 9 cell, 5 allocation, and out of 9, 5 allocation, and there are no allocation to 4 different cell. See cell number C12 no allocation, cell number C13 no allocation, cell number 23 no allocation, cell number 31 no allocation. This 4 cell has no allocation. So we have only 5 allocation, 5 non-zero. This is a basic feasible solution, and as I already mentioned, they are non-zero, rest all are 0. So why it is so? We have 3 sources, 3 destination, 3 plus 3, 6 minus 1, this is 5. So we have 5 non-zero solution. What is the solution we have got? X11 equal to 7, X21 equal to 3, X22 equal to 6, X32 equal to 4, X33 equal to 10. With respect to this solution, what is the value of our Z? The Z value is becoming like this: 7 into 1, then 3 into 3, 6 into 8, then 4 into 7, 10 into 6. Altogether, we have, say, 5 different cells. So with respect to the cell and the cost, we are saying the variables we have obtained. This X11, X21, X22, X32, X33, they are not the optimal solution. We have not checked whether it is optimal or not. They are solution. They are the trial solution, basic feasible solution. So what we have got using phase 1. But this solution may not be optimal. Unless you check, we cannot conclude that they are optimal. So we'll check for optimality. So presently the value of the minimum value of Z, that is not the minimum, value of Z is becoming 152 units. 152 units. Now, how do you find the dual variables? So as we know, X11 equal to 7. With respect to this variable, there is a dual constraints. The dual constraints U1 plus V1 minus 1 has to be equal to 0. Okay, so we have already mentioned like this. The dual constraint is like this. So U1 plus V1 minus 1 equal to 0, because the first one is non-zero. So U1 plus V1 minus 1 equal to 0. So here we find, so U1 plus V1 equal to 1 with respect to first one. Then U2 plus V1 equal to 3. Okay, so U2 plus V1 equal to 3. So, okay, this one, 3 is there. Then we have U2 plus V2 equal to 8. You can see here 8. Cost coefficient is 8. Then U3 plus V2 equal to 7. This is with respect to this. U3 plus V2 equal to 7. Then U3 plus B3 equal to 6. Okay, this. So we have altogether, as you observe, there are 5 such equations. 5 such equations. But there are 6 variables, 6 free variables. So here it is a assumption. One of the variable you can select 0. Let us say I am selecting U1 equal to 0. So after selecting U1 equal to 0, we can find a unique solution for this U and V, for the multiplier U and V. Okay. So what we are observing, U1 plus V1 equal to 1. Once you are setting U1 equal to 0, V1 equal to 1. Once this is V1 equal to 1, then U2 becoming, so okay, here V1 equal to U1 equal to 0, V1 equal to 1. So U2 plus V1, it's U2 plus V1, okay, that is a mistake here, okay. So U2 plus V1 equal to 3, U2 plus V1. So U2 plus B1 equal to 3. So once you are saying B1 equal to 1, B1 equal to 1, then U2 will be 2, not 3 here. U2 plus B1 equal to 3, B1 equal to 1, so U2 will be 3, let's see 2. Okay. Similarly, U2 plus B2 equal to 8. So U2 plus B2 equal to 8. So once you have got this, what? Once you have got this U2, we can find V2. And similarly, so in this manner, you can complete all these things. Here, some mistakes are there. Okay. So once you have got this value of U1, U2, U3, V1, V2, V3, so we'll check in this case. Okay. You can see here. Now, what is happening? U1 plus B2, U1 plus B2. So U1 plus B2, U1 plus B2. So it is giving as, let us say, so it is, let us say, it's giving 5, let us say. So what is that? It's not allocated cell, it is 9. So it is, of course, there is a mistake. So here it is, it has to be less than equal to 9, whether it is fulfilled or not. So less than equal to 9, it is fulfilled. I have put a tick mark. So U1 plus B3, U1 plus B3. So this U1 plus B3, U1 plus B3. So you can see here U1 plus B3, this is not allocated cell. It has to be less than equal to 2, but U1 plus B3, if you calculate, it is coming as U1 plus B3. So it is coming as 3. So 3 is greater than 2. This is not fulfilled. Similarly, U2 plus B3 equal to 6. So 6. And what is the cost coefficient with respect to this one? The cost coefficient is 4. So it is coming as 6. So it is greater. So it is not fulfilled. So first one is fulfilled. Second one is not fulfilled. Third one is not fulfilled. And the last one is fulfilled, U3 plus B1. So U3 plus B1, so equal to 3. So it is less than equal to 5. That is fulfilled, you can see here. Okay. So what we are getting? Generally, we are supposed to solve maximization type problem. But in transportation, we are solving minimization type problem. Minimization type problem. So what is happening to this? So maximization, minimization. So for maximization, we select the most negative element, Zj minus Cj. Here we are selecting most positive element, most positive in the sense, see 5 minus 9, it is negative. 3 minus 2, it is positive. 6 minus 4, it is positive. 5 minus 9. So only these two are not fulfilled, rest all are fulfilled. 3 minus 2, it is positive, 1 unit. 6, it is positive, 2 units. So most positive difference, it is giving this cell U2B3, U2B3. So U2B3 means, so second row, third column. This is, so with respect to this, we have, this is the entering variable. This is the entering variable. Once we are saying this is the entering variable, so with respect to the entering variable, we will form a closed loop by drawing horizontal and vertical lines. Each horizontal and vertical lines must be in a allocated cell. This, you know, the left side, the 6 is the allocated cell. Again, 4 is the allocated cell. Again, 10, where we mark join 10, that is also allocated cell. So once we have drawn a loop, so one point is written plus, means that is the entering variable. So plus, then we'll just mark something like plus, minus, alternately. The plus will be added, and when there is a minus, should be subtracted. So we will just observe how many negative elements are there. There are 2, minus 6 and minus 10. So how much you can reduce? We can reduce 6 unit. And how much you can increase? We can increase also 6 unit. So once you are subtracting 6, so the 6 will be 0 and the 10 will be 4, and are adding 6, wherever there is nothing, this plus, that will be 6, and this 4 will be 10. Okay, in this manner. So the new allocation is like this. Say this in the cell, the new cell, this is becoming 6, and below it is 4, and in the left it is 10, and one of them is 0. Now we like to know what is happening to this present allocation. What is happening to the present allocation? So we like to know. So how many allocations are there? In first row 1, in second row 2, in third row 2. There are 5 such allocation. So with respect to the 5 such allocation, so we like to find the multipliers. Find the multipliers U1, U2, U3, B1, B2, B3. See here. So U1 plus B1 equal to, see, U1 plus B1 equal to 1. You can see here 1. So if I am setting U1 equal to 0, U1 equal to 0, B1 equal to 1. Okay, this is gone. Then similarly, so we have here U2 plus B1 equal to 3. U2 plus B1 equal to 3. B1 equal to 1. So U2 equal to 2. And the same row U2 plus B3 equal to 4. U2 plus B3 equal to 4. So U2 equal to 2. So B3 equal to 2. So we have got. And in the last row, you can see here. So we have U3 plus B2. U3 plus B2 equal to 7. So U3 plus B2 equal to 7. And we have U3 plus B3 equal to 6 already. So B3 we have computed, that is 2. So since B3 equal to 2, we have U3 equal to 4. Once U3 you have got 4, so U3 plus B2, so that is coming as 4 plus 3, 7. So B2 equal to 3. So we have got U1 equal to 0, U2 equal to 2, U3 equal to 4, B1 equal to 1, B2 equal to 3, and B3 equal to 2. So please check these parameters, this what we have obtained is correct or not? This para correct? Hello? Have you checked this one? Now these are for the allocated cell, and which cell is not allocated? Now cell number 1, 2 not allocated. Cell number 1, 3 not allocated. Cell number 2, 2 not allocated. Cell number 3, 1 not allocated. With respect to cell number 1, 2, U1 plus B2, 0 plus 3, that is 3. This 3 is less than equal to 9. It is true. So it is fulfilled. So cell number 1, 3. So it is U1 plus B3, 0 plus 2. 0 plus 2 is 2. 2 is less than equal to 2. So that is fulfilled. Okay. 2 is less than equal to 2. It is fulfilled. So this is fulfilled. Next, cell numbers, say 2, 2. That is U2 plus B2. U2 plus B2, 2 plus 3, 5. 5 is less than equal to 8. That is also fulfilled. Okay. That is also fulfilled. Now finally, U3 plus B1, U3 plus B1, U3 equal to 4, B1 equal to 1, 4 plus 1 equal to 5. Okay. So this 5, okay, U3 plus B1 equal to 5. So 5, what is happening to this? This 5 is fulfilled or not? Is not fulfilled, because we have here U3 is 4, U3 is 4 and B1 equal to 1. Okay, so actually it is not 1, it's 5 is less than equal to 5. It will be 5. Okay, so this is also this right hand side, whatever it is not 1, it is 5. So this is also fulfilled. So please note, see right hand side I have by mistake I have put 1, it is equal to 5. U3 equal to 4, B1 equal to 1, 4 plus 1 equal to 5, 5 is less than equal to 5. Okay, that is true. So this is a feasible solution and all these primal constraints and dual constraints are fulfilled. So now we'll check the solution. So x1 equal to, you can see here, x1 equal to 7, x21 equal to 3, x23 equal to 6. Okay, and then x32 equal to 10, x33 equal to 4. Okay, we have got a solution. So with respect to this solution, we have minimum value of z equal to 134. And if you want to check the dual objective function, that is also coming as 134. So both are fulfilled. So that is a optimal solution. Okay, this is the conclusion. Is all right? Hello? Any confusion here? Hello? See what we have done. You are there or not? Hello? Are you able to hear?
Sir.
Yes, sir.
See,
Sir.
now if I am saying quickly that this is optimal solution, no further improvement is possible. Now you have to believe how. Because all these dual constraints are fulfilled. We have taken 4. Out of 9 constraints, how many are left out? We have taken 5. So out of 9, 5 we have taken, another 4 are left. So these 4 we are checking. So this is an optimal solution. Okay. So since it is fulfilled and we have got an optimal solution. Okay. So that is the conclusion. Now another problem you can see here. So this problem, so whenever you are checking, and if you suppose say we have got a solution, so we are checking, so whether this is an optimal solution or not. See 7, 9, 14, 10, 10, 10. So it is a balanced transportation problem. We are checking. So how to check? So we will calculate the value of the multipliers U1, U2, U3, B1, B2, B3. See here, if I'm saying U1 equal to 0, then B1 equal to 2. Okay. Similarly, say U2 B1, that is equal to 7. So since B1 equal to 2, U2 equal to 5. Then similarly here, you can see U2 B2 equal to 5, U2 B2 5. So B2 equal to 5. So U2 equal to 5, B2 equal to 0. Then we have in the last row U3 plus B2. So U3 plus B2. So our B2 equal to 0. So our U3 equal to say 1. Similarly, U3 plus B3 equal to 8. So U3 equal to 1, B3 equal to 7. Okay, this. Say we have got all the multipliers. So not necessarily always you should take U1 equal to 0. You can take B1 also equal to 0. You can take any variable 0, no problem. So or you can take constant also. They are free variables. But by simplicity, we are considering the first variable as 0. Okay, so that we can check the other cell. So whether their other cells are fulfilled or not, you can see. So with respect to the second cell, first row, second column, the cell number C12, that is U1 plus B2, U1 plus B2, U1 plus B2, it is 0, but it is given. So 9. Okay. So 0 is less than 9, that is fulfilled. Similarly, U1 plus B3, U1 plus B3, U1 equal to 0, B3 equal to 7, that is 7. 7 is greater than equal to greater than 4. So this is not fulfilled. Then U2 plus B3, U2 plus B3, you can see here, U2 plus B3, how much it is? U2 plus B3, U2 plus B3 is 12, 12 is greater than 3. Now, see, these two cells are not fulfilled. 7 minus 4, difference is 3, 12 minus 3, difference is 9. So that is the most positive element, difference is most positive here. So with respect to U2 V3, that is the entering variable. So the entering variable, we put a plus sign here, okay, U2 V3, okay. Now what is happening? So we like to make a closed loop in this manner. So that is plus, then in the cell 2, 1, that is a allocated cell, that is minus, then cell 3, 1, that is plus, then cell 3, 3, that is minus. We have a closed loop here. So this will be positive, this is the opposite one is negative, and these two are negative. So positive means it will increase, negative means decrease. We are making, say, a cell. So number of positive mark and number of negative mark cells, they are equal. These two will increase and that two will decrease. And as you know, 3 and 4, we can reduce 3 to 0, and 4 will be reduced by, reduce means it will be becoming 1, but the 6 will increase, that 6 will be, okay, and this one. So that is becoming positive here. So that is plus, okay, that is, this is the, okay. So as a result, we are finding a new allocation like this, okay. So U1, U2, V3, V1, V2, V3. So further we are checking. Again we find, say, all are not fulfilled, only 3 are fulfilled, say one of them not fulfilled. So we again make some allocation, and after that we find the solution, okay. So here, so the final solution we are finding, the multipliers are like this: 0, minus 1, 4, and that is the U1, U2, U3, V1, V2, V3, 2, minus 3, 4, and all are fulfilled, okay. This is giving the optimal solution, and our optimal solution, as you observe, so the minimum value of Z is becoming 77, and maximum of the value of Z dash is also becoming 77. So both are equal. So this gives the complete solution, okay. So I will stop here. So see the transportation problem. So the summary is like this: any transportation problem, check whether it is a balanced transportation problem or not. If it is balanced, find a phase 1 solution using either northwest corner rule or least cost method. After finding the phase 1 solution, check that it has exactly m plus n minus 1 number of positive variables. So if it has exactly m plus n minus 1 number of positive variables, means they are all non-zero, then it is possible to apply. Otherwise, it is not possible. So if any variable is becoming 0, you can set as epsilon, no problem, because assuming epsilon you can proceed and later on you can make 0. But if you are taking a 0, there will be some crisis. The crisis, as you know, we cannot find the multipliers U1, U2, U3, V1, V2, V3, etc. Because so exactly you need m plus n minus 1 number of allocation, because we have exactly m plus n number of 12 variables. Only one of them you can set 0, not 2 of them or 3 of them. Only one of them you can set until 0, because this will help. So after finding the multipliers, so you will check all the non-allocated cell using the duality theory, whether it is fulfilled or not. What is the fulfillment? Ui plus bj has to be less than equal to Cij. If if it is not fulfilled, then the constants are not satisfied. What will do? So ui plus bj less than equal to Cij. The left hand side is becoming more, right hand side is becoming less. Okay, so then it is not fulfilled. So we'll take the difference, most positive element we find. So that element is our entering variable with respect to that cell. So we'll form a closed loop. So drawing horizontal and vertical lines, every horizontal and vertical line, the end point has to be in an allocated cell. Okay, and number of positive marks and number of negative marks cells should be same. Then what we'll do, from the negative we reduce, from the positive we increase. So we try to find the departing variables. One of them is entering variable, one of them the departing variables. Then we proceed. Okay, and we have make it balanced in the sense. So if we are subtracting 10, twice 10 in units, then we have to add twice 10 in units so that it is balanced. Balanced in the sense, whatever you have subtracted, same amount we have added using the loop. So after completing the process, again find the multipliers and check whether it is optimal or not. If it is optimal, if it is fulfilled, it is optimal. If it is not fulfilled, the dual constant is not optimal, then you proceed. Okay, that is the rule. So with this, we completed the transportation problem. If you have any doubt, you can ask. Okay. After that, we'll move to the assignment problem. Okay. Any doubt? Hello? Please tell me. These slides, all the slides, whatever I have covered, I'll flash to you. Okay. So, if you are available, I'm telling here, already there is a notification that for the offline test, I have to submit the question paper. Okay. Right. For the offline test, I have to submit the question paper. Are you able to hear? Or any problem?
Yes, yes, you are audible, sir.
Audible or not audible?
Yes, audible, sir.
Audible,
Okay.
sir.
So already there is a notification for the offline test. So question paper will be submitted soon and they'll conduct the test. Okay. So this transportation is over, and as you know, from the all the section, so I will try to set question paper so that you will not face any problem. Okay. So even from the duality theory, from the integer programming, from the transportation, assignment, from every section there will be question, and the test is 2 hours. Okay, the IIT will conduct. Say we will also invigilate. So they have already given the time. I think you got the notice. You got the notice? Yes, or no?
Sir.
Okay.
Yes, sir.
So see, we have taken. I have conducted one test. They are midterm test. Okay, and assignment, other things I have already asked you to do, submit, and whatever you can do, that is all right. And that is the end semester test. So I will share the question paper and the test will be conducted. Okay. So first I should cover. So the 2 more chapters are left. That is, one is the assignment problem, another is the game theory. Game theory is very close to the linear programming. So very easily you can cover. So maybe next week we'll discuss about the assignment problem and then the game theory. Okay. Thank you. So if you have any doubt, you can ask me.
Sir, so end semester will have all the syllabus which was not covered in first test, right?
You have? Repeat.
So syllabus for end semester, sir, everything which is not there in first.
Generally, whatever you have studied, so more or less everything should be covered. Okay. Generally, otherwise 2 hours what will do? Okay, right? So you
Sir,
are saying that
question
should be
in first test will also be asked
No, fast test. What is there was something little about the linear programming and the basic feasible solution. So okay, so, all right. So yeah, you will not face any problem. The question will not be very tough, and the question, as you know, so everybody should be able to answer. Okay, everybody should be able to write. But as you know, this is not the objective. This is the subjective. So you have to solve a problem. Okay. So 2 hours. 2 hours means say let us say in 15 minutes one question certainly you can answer. Maximum I'm saying 15 minutes. Okay, maximum time. So accordingly we have. Okay, so both theory will be there, problem will be there. Okay, so if I'm asking a question like suppose a problem is given, formulate the dual program. So what is the difficulty? So you cannot. So you certainly you can do it. Okay, so like that. So the theory will be there, problem will be there. So you will not face any difficulty. So but you have to learn and you have to reproduce in the exam. Okay, thank you.
Thank you.
Thank you.
I'll stop here. Okay.
Thank you, sir.
Yeah.